Arithmetic facts are stubborn friends. It's all over for the Collatz conjecture if you agree that the nth terms of the Collatz map are arithmetically true. I'm going to read from a paper that I wrote and last revised on August 21st, 2023. The title of the paper is The Nth Terms of the Collatz Map, and I will explain how these two triadic nth term formulas are arrived at from beginning to end. The paper is short, it's only 5 pages, it shouldn't take too long to read. The nth terms of the Collatz map, Michael M. Ross. Abstract. Begin with a reduced or odd-numbered only Collatz map. Define 3 sets of positive integers and their corresponding functions, whose codomains are a modification of this reduced map. Observe that the intersection of the codomains are defined by 2 formulas. Then derive the nth terms for the odd integers and the even integers of convergence over the whole Collatz map. Iterate the 3m plus 1 function using the conventional formulation. For each consecutive odd integer, pair the input and first odd output. Define 3 disjoint sets of the positive odd integers. Set B is integers of the form a10 plus 1. Therefore, set B contains as its first few members 1, 9, 17, 25, 33, 41. These are the input integers of the bracketed pairs. Input 1, output 1. Input 9, output 7. Input 17, output 13. Input 25, output 19. Input 33, output 25. Input 41, output 31. Set D is integers of the form 4m plus 3. Therefore, the first few elements of D are 3, 7, 11, 15, 19, 23. These are the input integers of the bracketed pairs. Input 3, output 5. Input 7, output 11. Input 11, output 17. Input 15, output 23. Input 19, output 29, and so on. Set C is integers of the form a10 plus 5. So the first elements of set C are 5, 13, 21, 29, 37, 45. These are the input integers of the bracketed pairs. Input 5, output 1. Input 13, output 5. Input 21, output 1. Input 29, output 11. Input 37, output 7. And you see it appears chaotic. However, we will explain this. Define functions for B, D, and C for the output elements corresponding with each one. Well, the codomain of injective function B is given by B minus 1 multiplied by 3/4 plus 1. The codomain of injective function D is given by D plus 1 multiplied by 3/2 minus 1. The codomain of bijective function C is given by C minus 1 multiplied by 1/4 using an intermediate superset integer. This is the bracketed element in the following, which in each case is the first integer of a corresponding convergent sequence. So taking 13 as the input and 5 as the output, we can note that there is an intermediate superset integer 3, and we know that this is true because input 3 equals output 5. In the same way, input 21, output 1 has an intermediate superset integer 5, because we know that input 5 equals output 1. Input 29, output 11 has an intermediate integer 7. And we know this because input 7 equals output 11. Input 37, output 7 has an intermediate superset integer 9. And we know that input 9 equals output 7. 45 has an intermediate integer 11 before reaching output 17. You don't see that 11 unless you take 11 as the first input, in which case the output is 17. So I hope I've elaborated a little bit on what these superset integers are and how important they are to solving the conjecture. So this is a modification to the reduced Collatz function OEIS AO75677. Now, odd integers except for multiples of 3 are elements of codomains for function b and function d. Thus, for the function b minus 1 multiplied by 3/4 plus 1, we see the outputs are 1, 7, 13, 19, 25, 31, 37, 43, and so on. For the function d plus 1 multiplied by 3 divided by 2 minus 1, we see the outputs are 5, 11, 17, 23, 29, 35, 41, 47, and so on. For the codomain of the function of set C, we have all the odd integers, including multiples of 3, as the outputs. So for C minus 1 divided by 4, input 5 is output 1, input 13 is output 3, input 21 is output 5, and so on. 1, 3, 5, 7, 9, 11, all the odd counting integers. This is the bijection, and these are the superset numbers. One may, of course, express the foregoing functions in a conditional equation. So for the first case where n equals 8k plus 1, where k is any arbitrary integer, positive integer, m minus 1 multiplied by 3/4 plus 1 is the function that is applied. For the case of n equals 4k plus 3, we apply n plus 1 multiplied by 3 over 2 minus 1. And for the third case, if n equals 8k plus 5, we subtract 1 and divide by 4. And the order of operation is set by the order of the consecutive input elements, such that the first element, 1, belongs to set B, the second element, 3, belongs to set D, the third element, 5, belongs to set C, and the fourth element, 7, belongs to set D, and so on. So it's always B, D, C, D. The elements of the codomains of the functions for B, D, and C are equal to and in the same order as the set of all points on the modified reduced Collatz map as published in OEIS A324036. From the above statements, we can derive two formulas that describe the intersection of the codomains of the functions for C and B and C and D. These formulas are C subscript 1 equals 3B plus 2, and C subscript 2 equals 6D plus 3, such that C1 are the elements of C of the form 24n plus 5, and C2 are the elements of C of the form 24n plus 21. These formulas also define in every case the convergence of two odd sequence numbers on one even number. Thus we have triads, of which the basis case is 1, which belongs to set B as the input, has an output of 4, and 5, which belongs to the set C subscript 1, also has an output of 4. So they converge. And they converge according to this formula, C subscript 1 equals 3b plus 2. We can now derive for each formula the nth terms for pairs of odd numbers and their even number of convergence. For the intersection of the codomains of the functions for set C and set B, using C subscript 1 equals 3b plus 2, we see the first case is the one already cited. C1 equals 5 and B equals 1 merge on 4, which is 5 minus 1. The second instance is C1 equals 29 and B equals 9 merge on 22, which is 29 minus 9 plus 2, as represented in the diagram as well. In the third instance, we have C subscript 1 equals 53 and B equals 17 merge on 40, which is 53 minus 17 plus 4. And the next one is C1 equals 77 and B equals 25 merge on 58, which is 77 minus 25 plus 6. From this, we can easily derive and directly derive the nth term formulas, which are the nth term of C subscript 1 equals 24n plus 5. The nth term B equals 8n plus 1. And the nth term of the even number of convergence is 18n plus 4. And we can immediately verify that this must always be the case for C subscript 1 equals 3b plus 2. If we consider that C1 times 3 plus 1 divided by 4 will always equal B times 3 plus 1 divided by 4 multiplied by 3 plus 1. For example, if C1 equals 101 and B equals 33, 101 times 3 plus 1 divided by 4 equals 33 times 3 plus 1 divided by 4 multiplied by 3 plus 1. So this is the first intersection. The second intersection is for the intersection of the codomains of the functions for set C and D using C subscript 2, C2 equals 6D plus 3. The first instance is C2 equals 21 and D equals 3, merge on 16, which is 21 minus 3 plus 2, as set forth in the diagram. The next instance, C2 equals 45 and D equals 7, merge on 34, which is 45 minus 7 plus 4. C2 equals 69 and D equals 11, merge on 52, which is 69 minus 11 plus 6. C2 equals 93 and D equals 15, merge on 70, which is 93 minus 15 plus 8. We can define the nth term formulas as C subscript 2 equals 24n plus 21, and D equals 4n plus 3. And the even number is given by 18n plus 16. And we can verify that this must always be the case for C subscript 2 equals 6D plus 3 if we consider that C2 times 3 plus 1 divided by 4 equals D times 3 plus 1 divided by 2 times 3 plus 1. For example, if C2 equals 117 and D equals 19, 117 times 3 plus 1 divided by 4 equals 19 times 3 plus 1 divided by 2 times 3 plus 1. So we now have the two sets of nth terms. In each case, there's two odd terms and one even. Finally, we are left with a subset of odd integers that are not members of the nth terms. This is a small subset. These are numbers of the form 24m plus 13, the first elements of which are 13, 37, 61, 85, 109, 133, and 157. However, it is easy to verify that these are joined with a subset of the even nth terms of C1 equals 3b plus 2. The even integers are multiples of 18n plus 4 of the form 72n plus 40. Thus we have a function 24n plus 13 times 3 plus 1, which produces input 13, output 40, input 37, output 112, input 61, output 184, input 85, output 256, and so on. The system has no dynamical variables that need to be accounted for.